Shall we start the session? Sir, shall we start the session?
Yes, we can start. Am I
You
audible?
You
Okay.
can start.
So let's share the screen. Okay, hello everyone. Is the screen visible to all?
Yes, screen is visible, but you just go to that particular document so we can.
Yes. Okay, so we will start our lab. So we will move to our website. So you must be already having already having the link for the website. So we will begin with the lab. So today we will not be indulging into very much into code or heavy implementations. We will lay the foundations for upcoming labs. So we will be having a brief discussion on what we will do today and in upcoming 9 days. And the major task for our today is to have one implementation for a very uh, traditional attack. So we will go step by step. So let's begin. So here you will be able to see the download button. From here you can download the entire files for this lab. So when you will download, it will basically have a zip file which you can open. It will have all the contents. I already have that downloaded in my system. So starting with, where does this today's session fit in the entire 10-day landscape? So first of all, today we will start with setting the environment, Python environment basically, because we don't want to mess our global libraries and local libraries together. It has a bad impact on our code implementations. So it is a good habit to have your own virtual environment for all of your private projects. So we will basically first see how to set our virtual environments, and also we will see the most important libraries which we should be knowing to conduct the entire 10-day practical implementations. So for everything, we have some open source libraries, and throughout the session, we will also implement some of the codes by our end. And whenever we will be good with the implementation, we will use third-party open source libraries to implement that particular component. And the next thing that we will do in our today lab is to have one real attack implementation. So name of this attack is FGSM attack. So it was published in 2015 in ICLR. Let me uh, uh, then we will go with the map of the entire 9-day labs that we will be performing, what we will be doing in each day, and what is the rationale behind all the labs that we have in sequential order in all 10 days. So here are the names of the different labs that we will having in the 10 days. We will brief on them in the end of the lectures. So without delay, let's introduce the first section of our today's lab, that is the tool setup and all the libraries that will be required for this entire FDP. So first and foremost important is your computer and your Python libraries. So for computer, you also need to work on LLMs, on heavy models. So you should have at least some access to GPUs. If you're not having access to GPU, you can go to the Kaggle. They offer you somewhat around 30 hours of limit for the GPU, and you can also go for Colab. So those two platforms are pretty good to provide you free GPUs. So basic amount of GPU is required for this FDP. Now the next thing is that we need some understanding with the Python. You should have basic knowledge of uh, basic code implementations, what are functions, what are definitions, how we implement some basic functions and all that. Next, we will require PyTorch and Torch Vision libraries. These are pretty much very famous libraries in entire MLDL landscape. So this was introduced by Meta basically. Initially, it was much popular in the research domain, but now it is also very famous in industry as well. So it contains everything that you require in the entire pipeline of DL implementation, from code to data sets and everything. You can also implement your custom AI models as well from this PyTorch. Next, we have some custom libraries for implementing attacks, different type of attacks. That is Torch attack library. So it provides you pre-implementations of various types of attacks that are already addressed in the academia. So we will also see how to implement our attack by our own code implementation, and also how you can implement with the help of this library. And next, we also need a few privacy and teamwork related libraries. The most famous out of them is Opacus. So basically, when you are dealing with privacy related stuff in DL, you stumble upon differential privacy. So it is best implemented by this library, which is Opacus. And this is a very famous library in domain of distributed learning for implementing FL, that is Flower. So with the help of Flower, you can basically have implementation for federated learning. And then for implementing large language models, we have very famous library which is Transformers. So Transformers is provided by Hugging Face, and it provides a lot of utilities for you to easily implement LLMs. Next, a few additional libraries we have. This is Art one. This is also an extension to what you can say Torch attack. It also have a lot of attacks and defenses pre-built, and uh, it was provided by Meta for no, I guess it was provided by IBM for benchmarking and all that stuff. Rest all are pretty trivial libraries like scikit-learn. So basically these are all the set of libraries and modules that you will be requiring for entire 10-day session for our FDP. So you should have some basic familiarity with these libraries. Also another thing, after each section we are having some quizzes. So for just to be interactive purposes, we can have some quick quiz to understand what we are on the same page or not. So like very basic stuff, why do we make a separate virtual environment? So to keep the project separate from the rest of your system, that's it. And the next, which one thing do all the attacks in this FTP rely on? So that will be our gradient from AutoGrad. So it was some kind of a miscellaneous question. So basically after each section we are going to have some quiz, and we will have some interactive sessions there. Now moving on with the first part of our today's lab, the agenda, that is to set the entire system setup, that is to say our environment, virtual environment, to download all the packages which are required. So I will highly suggest you all to open Google Colab. So you can just simply, what you can do, you can go to Colab, log into your ID, and you must have downloaded your this file from our page uh, here. So you will get a .ipynb file. So you can import this here, and you can run all the code here. So that will also be good for you. You can see how the code is implemented in real time, and it will also make the conversation twofold. So let's move. So the first part of our code is to implement the virtual environment. So you can simply run this code in your Google Colab, and see how your virtual environment is set up. So it will make a virtual environment where all your local libraries and modules will be downloaded. So it will not collide with your global libraries. So it will set you free from all the collisions and all the hassles that you feel during the code implementations. Now, next very important part of the setup is this file, which is requirement.txt, and it is a very good habit to have this in your overall code folder. So what you can simply do is list down all the libraries and packages and their versions, and you can provide this in your code base. So anyone who wants to replicate your code base just simply have to run this command, that is pip install r requirement.txt, and it will have all the packages and modules of the same version from which you have implemented the code downloaded on your in his computer. So this is a very good practice for a reproducible code. You should always have this requirement.txt file, and this is a command how you can run it. So the next part is how you check exactly your environment is having all the packages or not. So this is a small code snippet. It
Sorry to
is,
interrupt you.
yes,
Can you zoom it little bit so we can easily, it's visible board.
yes, sir.
Can you zoom it?
Okay, okay. So is it good enough?
Now it's fine.
Okay.
Now continue. Continue, sir. Now it's fine.
Okay, okay. So here is the next code snippet. So it will tell exactly your environment is having the required packages and libraries or not. It is not mandatory, but you can have that. So you have a peace of mind that you have all the installed libraries and modules or not. And this is what your expected output should look like. You can run this entire thing in your Colab notebook. This is a Colab notebook, and you can run this piece of code here. So you will get something like this. So this was basically all the basic setup that you need to do. It is quite common practice while implementing the code, not a very big deal. So next we will move to our important section to give out the rationale exactly how these attacks happen in an AI model. So first of all, we will have to understand exactly what is the life cycle of an entire training process of an deep learning module. What are the phases? What are the components? And exactly what are those components where we can slip out our triggers and our methods which alters overall deep learning model. So here I have a diagram for you. So you can see the first step that you are having is training data. So in the training data, what you are having is the input, which can be a picture and a label. Basically, what that input label signifies. So this is your training data. and intentionally this is split into two parts, that is input and labels. And I will tell you later what these numbering exactly means. So next part is the model guesses, that is the forward pass. You pass the input to the model, it performs a forward pass, it comes with some type of a prediction and calculates what is the loss. So basically loss is basically to understand for the model how far it is to the actual prediction. It is a mathematical entity and you can have different types of loss. For example, for classification tasks, you have cross entropy. For regression tasks, you have various types of loss functions, RMSE and all that. So you calculate loss here and then calculate the gradients, which are basically the change of this loss with respect to that particular weight. And then you pass that into an optimizer which updates your weights. So this is basic pipeline of your deep learning training module. So you have training data, forward pass, loss, gradients, and update. So you run this entire pipeline again and again, which is basically your iterations batch by batch. And what you get at the end is a trained model. So a trained model is basically has learned all the distribution of your input training. So now we need to build some rationale that exactly where we can slip out our all attack mechanisms. So there are five places where you can put your attacks. So one and two, that is the first and the second part where you can slip your attack are on the input and the label part. The third place where you can inject your attack is on the gradient part. You can manipulate the gradients. Fourth part where you can introduce your injection is basically weights. You can alter the weights of the model. And finally, you can also evade the model even the model is trained, even then you can evade the model. So basically these are 5 points where you can inject malicious behavior into the model. So this figure is very important. It gives you an idea basically where you are going to introduce attacks to the overall framework of the training. And each category, each part, you can have different categories, and each category can have their own mechanism, which we will discuss further into the session. So next part is basically description of this entire thing, 1, 2, 3, 4, and 5. So if we talk about the technical terminologies of these all components where we are going to inject attack, so these are mentioned here. So the first, when we introduce trigger into the input data, it is called poisoning the training data, basically poisoning the model. So what do, you slip out a bad example into the model training data and try to manipulate the model to learn that bad samples. Next, this is also before training, that is you tamper with the labels. You basically have input example as a cat, but you label it as a dog. So naturally model will be manipulated in its own training distribution and to identify the final answer. The third is basically introduced during the training. So these two was before the training. Basically you manipulated the input and the labels, and then this is the part which you introduce during the training. So what do you do basically when it is training, it is producing gradients, you are going to manipulate those gradients. It is very common in distributed learning trainings like FL. In FL, there is common practice. There are some malicious clients and they are going to mislead the gradients that are going to the central server. And then it is the fourth component, which is that is weight tampering. So this is also kind of after training component. So when your entire model is trained, you get a set of weights of that model, and then what you are going to do, you are going to manipulate those weights. Basically you are going to alter those weights in favor of your adversary themes. Then there is this fifth part, which is the evasion component. So after entire model has been trained, still you can manipulate the model to identify input into a wrong output. And today this is going to be our focus. We are going to implement this attack today. This is going to be our prime target. So basically what we are going to implement is this thing, which is FGSM method, which is fast gradient sign method. So now let us move to this attack implementation. So before moving to any details of the attack, let me show you the exact paper. This paper was introduced in ICLR basically. So name of the paper is explaining and harnessing adversarial examples. So it was published in ICLR 2015. It is a very prestigious conference. It is a A-star level conference, a very renowned conference in AI. And this fellow was the author of this paper, which is Ian J. Good Fellow. It is a very renowned personality in artificial intelligence having lakhs of citations. So the basic idea of this paper, what the author have suggested is this equation basically, or you can say this component of the equation. We will break this equation step by step in upcoming part. But to give you the rough idea, what they are doing is you have this input image. Okay, so you now need to evade your model to answer it incorrectly. Even though the model is trained, still it is going to identify this input into a wrong output. You see here input label is panda, so naturally model should output it as panda, but it is not identifying it as panda, rather it is saying it is a gibbon. So gibbon is basically a species of apes, so it is saying it is not a panda, it is a gibbon. And interestingly, it is saying 99.3% is confident that it is a gibbon. So what exactly mysterious thing that they have done in the middle is the part of our study, and this is the part that we will going to implement today. So just a rough idea, what they have done is they have introduced this rough noisy patch, which they are going to merge with this image, and you will not be able to visually see that this image is basically tempered. So this is merged with this noise and it gives this answer. Now, one very interesting fact about this thing is when you just provide this as input data, like this noise to your model, what it is outputting is nematode, which is basically a worm. So you must be saying it is completely random, but for a deep learning model, which is a mathematical machine, it identifies it as a nematode, which is basically a worm. So overall, the context of this image is that you input panda merged with the noise, which looks like worm to the mathematical model, and when you merge them, it says it is a gibbon. So basically, this is an interesting part of this paper. So we are going to implement this thing. So what they have overall done is after the training, you get a model. You are having an input image. You are having a noise which you are going to merge and put that into the model, and it is going to output a fishy output. So it is basically very dangerous. Like if you think you are having a self-autonomous driving car, you have trained a model on thousands and lakhs of images, and when you are driving it, what someone does it, there is a stop light, and what they are going to do is they are going to introduce some noise in that stop light figure that you are having in the sideways, and your car is going to suddenly brake or is going to suddenly accelerate. That can be a very dangerous thing. So this is a very severe case of an attack. So now let's move back to our slides and exactly see the details how this attack is being implemented. So the basics of a deep learning is that you simply introduce your input sample. It processes through the neurons and outputs a probability. Basically, what the output is going to be. It is having some tensor multiplications operations here in the middle and is going to output some probabilities. So this is the basic which everyone is quite familiar with. Moving with, we will understand the core equation which is behind this attack. So I want you to visualize this equation into two parts. This is the adversarial input image, this is clean image, and this is the noise that we are going to add, and this is the point of concern that is that this attack is basically introducing into the input image. So when you are looking to this equation that the author has stated here, this is precisely that equation. So what this equation is doing basically, it is having a component which is epsilon, and then this function which is sine derivative of loss function. So this is basically loss function with respect to input and label, and it is calculating derivative and encapsulating this inside a sine function, and it is capping the sine function with the help of this epsilon scalar value. So we will look into details why exactly each component and what is the relevance of each component. But before that, rough intuition what exactly this equation is trying to achieve is, normally your training should make the error go down. So while the training, your error should go down, but what this equation tries to do is that it naturally tries to make your error go up in upper side of the landscape. So this is what, in very layman terms or high level intuition, this equation is trying to achieve. Now, here I have a visual representation of exactly what the overall thing is happening. So here you can see this is a file which is in pixel format. You are having some tiny noise which you will have here, and you will get a final adversarial image. So this entire visualization is based on this image, this equation. So you can also try that in your web view. Here when you will increase this bar, you will see model recognizes is at digit 5, but when you increase it to a certain part, it suddenly starts to recognize this input as 3. So what is the rough value that it starts to recognize it as 3 is something around epsilon of 0.14. So it has relevance here. Means if you increase this value, it is going to be more confident in misclassifying the output. And if it is less, it is going to have the appropriate output that we are considering. And here you can also see the confidence level, like how confidence it is to say that the output of this input image must be 5 or 3. So when you increase the epsilon value, it is very confident that this is 3, not 5. So now with this rough idea on how these things are changing, we will go and understand this equation. So Nick, in this equation, what we are going to do, what we are trying to do is, we are having pixels. Like these are pixels 1, 2, 3, 4, and 5. What we are going to do is introduce a noise in each pixel. But now there's a question, you can introduce now noise in a very random fashion. If you are going to introduce noise in a very random fashion, what it is going to do is it is going to cancel it out. So basically, this is going to be a positive noise. Maybe it is negative. This then again it is positive. Then it is again negative. So what it is going to overall affect is that overall magnitude would be 0. So introducing random noise is not something that we as an adversary need. We want a very directional way to introduce this noise. So this part, that is derivative of this loss function, basically acts as the compass. It tells you what, in which direction your noise should basically proceed. It should not be a random noise, because random noise is going to cancel it out. Now the next question is, why this sine function? You can remove this and can directly multiply this with the epsilon. So why we are going to do is that we need to cap this entire thing into one magnitude. Like the problem that we addressed here, there can be a positive noise, there can be negative noise, and there can be again a negative noise. We don't need this. We need a coherence between the magnitude so that pixel noise does not cancel out each other. So we are having this sine function here, and this entire thing is multiplied with epsilon, which is a scalar value which you can manipulate by yourself, which can be small as 0.02 or it can be high as 0.22. So basically it is like a signal to the attacker how aggressively you want to perform the attack. So it has downsides. If you are going to keep it too high, what will happen if you keep it too high? If you are going to keep it too high, you will see visual differences in the input, and it is going to be easily catched by the model basically. So you don't want that. You want that your noise should be in such range that it effectively awaits your model. Basically, when you are having in this range, you are seeing this is very close to the output. They are very nearly very small changes in the input images which are causing this attack. So this is the entire rationale behind this equation, and this equation is basis for this entire attack. Now, next, move on to a concept which is linked with this attack. So, why exactly this attack is basically working? So, when you see a ML model, it basically learns a distribution. It is a high dimensional distribution, and that high dimensional distributions, there is a distribution boundary which separates labels from one to other. So in high dimensionality, they are very close to the edges, that is decision boundary. So like this is the decision boundary and this is the label. So this label says it is a panda and this part says it is a gibbon. So when you push the image into a certain direction, what happens is basically your point for that input feature gets shifted to that other side of the boundary. And this is the reason why this is attack is working. So in a nutshell, what you can assume from this equation is that you are going to update the input pixels in such a manner that it is going to shift your input features up, push that towards the edge of this boundary. So that is the high level why this attack is basically working. Now let's move on to the code implementation. So I have this code, very basic code to implement this entire attack. So first I will give you a brief on entire components of this code one by one. So here you can see we are we are importing all the important libraries, data sets and everything. Here we are importing torch and torch.nn, which is for neural networks. Then we are importing torch vision, which is very helpful for downloading data sets that we need for training and other stuff. Then we are having data loader, basically load the data into the model. So these are basic packages which will be required to run this code snippet. Then we have this second component of the code, which basically tells our system if you are having CUDA installed, basically GPU support, you can run on that. If you're not having, you can run that in the CPU. So basically this second component is telling your system to run it on CUDA or CPU, depending upon the condition of your system. Then here is a small function, class, which is having two functions. So it is specifying a very simple convolution neural network. So these are the CNN layers, that is the conv layer 1 and the conv layer 2, and this is the fully connected network. And these are the parts of the forward propagation having ReLU as the activation function. So it is basic implementation of your CNN, nothing new. Then this part of the component is basically about loading the data set. So data loader is the function which is loading the MNIST data set. It is having some transformations, and this is dividing into batch size of 128. So basically what the batch size is clubbing out your input for the loss. So basically it is like batching your input to be processed towards the model. So this is one component. Then the next component is the training loop, how training would be performed. So here you have initialized the model that we have made here, that is this one here. Then we have defined the optimizer is Atom. You can select different types of optimizers here. You can have Atom, you can have all different types that are there, Atom, W, or other ones. Then this is a loop. So basically a loop for your training. It operates batch by batch. So what this loop does, it takes your input and the labels and feeds that into the model, calculates the gradients and calculates the loss, and repeats this process in iterative fashion inside this loop. So this is the training component. Then this component is the attack component, and it is the center of our design. So basically it is a definition for FGSM, that is our attack. So there you are having 4 lines. First line, it is having three basic uh, classes. First, it is having input and you are cloning it because you don't want to make changes in the original image. You don't want to override that. So you are cloning that input. Then you are detaching its gradient history. So basically, whenever there is calculation of gradients, it calculates a computational graph. It is inherent in your PyTorch implementations. So you don't need that. So you detach that computational history of your gradients, and then you are having this parameter which is requires grade true. So basically, why this is important, because all the gradients that are calculated in PyTorch by default are calculated with respect to the weights. So you don't want that. You want the gradients with respect to the input image. So basically what I'm saying is, in this equation, you are seeing that we are calculating gradients. We are calculating gradients with respect to the input image, not with respect to the weight. Basically input image pixels. So this part takes care of that. So what first line is doing, basically it is cloning your input image, it is detaching its computational graph, and it is initializing the gradient with respect to the input pixels. So this is what this first line says. In the second line, we have basically the loss that we are going to implement here. It is a simple cross entropy loss. So this component, this one, that del x thing, this is the loss, and it is cross entropy here in our implementation. Then in the third line, we have the main equation. We are having input image. We are having this parameter that we can define on that we can define by ourselves, and it is multiplied with this gradient basically, and encapsulated in that sine function. Basically, this equation is computer implementation of this mathematical equation. And finally, fourth line, it is returning this adversarial input images back to this function. And again, we are detaching. The reason is same. We don't want the computational history of this gradient to be forward to the next basically attack gradient history. So we are again detaching this. So this is the basic function that we need to implement by our own hand. So you can also implement this attack with the help of a library, which is this one, torch attack. So this is a simple one line implementation. What you're going to do is, from torch attack import fgsm and x of adversarial encapsulated in the fgsm function, and you can specify whatever is the epsilon. So since we are going to do hands-on, so I have given you a code snippet exactly how you can manually implement this attack. And next component of the attack is trivial, that is defining your clean accuracy and your attacked accuracy. So this function is all about that. It is going to take the model and is going to perform the eval function. So what it is going to do here, it is going to run in a loop. It is going to take your input and output, and there is a condition. If it is an attack input, if it is an attack input, it is going to perform the predictions and basically going to score your based on this equation, and is going to return you your accuracy and under attack accuracies. So it will look something like this. So it will give you clean accuracies and under attack accuracies basically for different values of epsilons. You can see here for 0.05, it is basically very good, 92.5%, not affecting much of this this model evasion. But as soon as you are going to increase this epsilon to 0.3, you are going to see it drops down to almost 10%, which is almost equivalent to guessing like digits from 1 to 10. So this is the entire code snippet that you should run in your Colab notebook. So what you can do is go to your Colab notebook, uh, initiate your runtime. You can simply run this in CPU. I am not using GPU here because you are going to run simple CNN network. So you can run it anywhere. This is the code snippet that I have briefed you, our entire components, and this is something what it should output. So you can see at 0.05 Again, it is getting 92. At 15, it is getting 59%, and 25, it is getting at 18, and at 30, it is getting only 9%. So you can implement this entire code snippet into your collab notebook. So I will wait 5 minutes here. I will let you implement this. And for the time being, if you have any doubts, you can ask me. Then we will move to the next sections. Okay, so let's continue. So, do you guys have any questions till now, or are having any difficulty in implementing this code snippet? You can ask me in the chat. Okay, so basically dot detach. So Ahan, what basically we are doing here is when we are training a deep learning model, so it is inherent property of your PyTorch to prepare a computational graph of your gradients. When you see gradients mathematically, that is basically a chain of derivatives. So when you are implementing this in a computer, so PyTorch, what it does, it creates a computational graph. So it keeps history of all the prior steps. But since we are performing this attack after your training happens, you don't want those computational graph to collude your current gradients basically. So for the purpose, what you are going to do is you are going to cut off that computational graph of those gradients and only going to keep the current gradients, and it is not affected by prior gradient graph. So that is the purpose of this detach function. So I hope it is a bit clear. So any other doubts? Okay, so we will move to the next section. So for today, this was the only part of the code implementation that we are going to do. from tomorrow onwards, we are going to be in rigorously into the code implementation. I don't want to make it very heavy on code implementation from the first day itself. So today, basically, a basic overview of entire thing. So today we have implemented this attack, which is a evasion type of attack, and you can run this in your notebook and understand all the components. So what I want to tell you is there entire attacks that we are going to conduct from here on, those are going to follow similar structure. You are going to have these components common in all those attacks. You are going to implement your model data loaders, training loops, and this accuracy functions. So these are going to be very common. The only thing that you are going to change is basically some functions. You are going to write them by your own hand, and those functions are basically manifestations of your mathematical intuitions. So this is a very minimal code snippet, but will act as a compass for you in the future lectures to how to write a attack code or a defense code. So I want you should go through this code again, understand all the components. These are very basic components, but understanding this component will build the basics that you need for further lectures in our FDP. So okay, next we are going to have quiz. We have two questions, very easy questions based on the entire discussion we have had here. So the first question is FGSM. Which way is each pixel moved? So I have talked about this also. So I want you guys to write your answers in the chat. So what is the direction in which pixels basically move? So this is the question. So what are your answers? Any reference book about the methods and functions. So basically you are, if you are talking about just Python implementations, then you can refer to orally books. Those are very standard books, and though those books have very good explanations and everything. So you are going to get every basics that you need for Python there. So orally books are really great books for that. Name of the book, I will attach that at the end of the session. Okay. So any answers? We are having this first question. Please write your answers in the chat. What are your opinions? Where will the pixels move? C and D. Okay. So basically you are saying that direction that lowers the error, and B, the sign of the gradient, the direction that raises the error. Okay. Any other answer? C, raises the error, direction of the error. C. Okay, so majority of the guys you are saying is basically answer C. So let's see, it is the correct answer. So basically what the point of this attack was to push your pixels in the direction where error is maximum, not lower. So this function of lowering the error is basically the function of your optimizer, not the attack. What our attack is doing opposite of the training optimizer. It is going to increase the error, not decrease the error. So B is not going to be the answer. C is the correct answer. So now we will move to the next question. That is, the attacked image looks the same to us but is misread. Why? So we have also have discussion on this. So what are your guesses for this question? Please reply in the chat. Second question is B. Okay. Tiny push crosses with. Okay. Okay. So B and D. Let's see. So some of you are saying it is B. It was already near the boundary the model uses. So a tiny push crosses it. And some of you are saying C option, the model was never trained. So let's see. Okay. So B is the majority, and that is the correct answer. We have already discussed on this part. Basically, in your multi-dimensional representation of these vectors, there is decision boundary, and these features are very close to that decision boundary. If you are going to push that feature vectors, basically pixels, with the help of that gradient, which is moving it, making its error high, it is going to push that from this error boundary to other side. So that is the reason you are not going to see major differences in the input, yet it is misread by the model. Okay, so we will move to the next section of our lecture of lab, which is the whole landscape of the AI attacks. So before moving to the code implementation in further labs for all the attacks and defenses, we need to have some rough estimation of what exactly we are going to implement and what is the need of those implementation. We are supposed to have a mind map of what is the entire landscape of attacks and what are the defenses pertaining to those attacks. So I prepared a basic graph. This graph basically sums up most of the attacks that are there in the academia. So moving on with the evasion part, we have evasion, we have poisoning, we have backdoor, we have privacy, we have model theft, we have prompt attacks, availability attacks, supply and agent attacks. For each component we are having multiple types of attacks. So this is a vast landscape, and in the next coming 10 days we will cover some part of these subcomponents, so you get a holistic picture exactly what is the attack and defense landscape on AI and for AI security and security for AI basically. So starting with the first component, that is evasion attacks, we will see what are different subcomponents of these attacks. So we have three sub attacks here, that is FGSM attack, PGD attacks, adversarial patch attack, black box transfer attack. Before moving to the details of these attacks, I want to ask a question basically. Do you find anything which is limiting this FGSM attack? So this attack is not a perfect attack actually, and the reason behind this attack is not a perfect attack is that it is using this equation, the equation, very equation, which is the central for this attack to work is also its limitation. So basically, if you closely watch this equation, it is a linear equation. So what it is hypothesizing is that the entire DL landscape is linear. But you all know when you are calculating loss, it is not linear. It is highly non-linear landscape. So in cases where your loss is very non-linear, this attack is often failed or does not work very well. So to mitigate this limitation, we have next type of attack. This is a PGD attack, which is uh, projection gradient method. Next, we have adversarial patch, where what we are doing is we are having a small patch in the input of the image, and it is going to manipulate the model to misclassify. And the next part of this evasion strategy is black box transfer. So you all must be knowing that these DL models have capability of transferring their knowledge learned from one task to other models. So in these type of attacks, what we are doing is basically we are creating a surrogate model. So you can consider surrogate model as a clone model of the model to which you want to evade. So you are going to make a surrogate model, and with the help of that surrogate model, you are going to attack the main model. So these are the attacks that we will cover on day 2. So these are the all the types of attacks we will address in tomorrow's lecture. Next part of our component of attack is poisoning. So it is also having some landmark subcomponents which are label flipping. What you are going to do in this type of attack, you are having input of cat image, but you are going to say you are going to corrupt the label. In for the cat image, you are going to label it as dog, and for the dog, you are going to label it as cat. So naturally, what you are going to do is manipulate the model to classify basically wrong labels. So this part comes into label flipping. Next, we have clean label poison. So you are not going to flip around the labels, but you are going to introduce a small change in the input feature of your image. So basically poison that still looks normal. So label is not changed. Input is also not very much changed as far as when you are looking naturally to the image, but it has some features which are having malicious component in them. Then there's availability poison, which is whose main motto is to break the overall accuracy of your model. So what you are going to do is you are going to introduce some corrupt input data into your training samples, and your overall objective is to break the overall accuracy of the model. So these data poisoning strategies we are going to discuss in the day 4. Then we have backdoor component, which is also our part for day 4 and day 5. Here we are going to discuss these three types of attacks, which is bad net trigger. It is a very landmark attack, and you will find it in a lot of academic works. So it is what it does, it basically introduces a small patch in the input image. It can be centralized patch or it can be a decentralized patch, basically distributed in the entire of the image. So what this patch is going to do is manipulate your model into misclassifying your output. Then there is Trojan weights. That is a shared model, but what you are going to do is corrupt its weight. Then finally we are having FL model poisoning. So FL is a very prominent distributed training. So there what you are going to do is manipulate the gradients which are going to be transferred to the central server. So because of that, a single client is going to corrupt the entire global model that is situated on the server. That is something that we will discuss on day 5. Next, we have privacy component. For privacy, we have 4 implementations that we are going to discuss on day 3 and day 6 and day 5. So first one is the membership inference attacks. So objective of these attacks is to basically classify whether the particular training data point was available in the training data set or not. So let's assume you have a medical data set and you want to identify whether your record was there in the training data set or not. So where are you going to run this attack? So it will basically tell you if your particular data point was there in the training set or not. Now next is the model inversion attacks. What do you do here? You are going to reconstruct the input features from the trained model. So like I have this vision models and I am going to reconstruct my features, and with the help of that I am going to roughly construct my input data point. So next subcomponent is training data extraction. So here what you are going to do is you are going to repeatedly query your LLM, and your objective is to basically extract out the repeated memory that is there in the LLM. It is famous for LLM. So like you can assume there is a sensitive phone number, addresses, sensitive information basically, and with the help of queries you are going to extract those information from the LLM. Next is the gradient leakage. So again, it is very famous for distributed paradigm. You have FL paradigm, and clients are sending gradients to the server. You are catching those gradients, or your server is malicious server. It is going to take those gradients, and with the help of those gradients, it is going to reconstruct the private data points. So in all these 4 components, all these 4 types of attacks, you must be seeing a common theme that is about the data. So this part is basically about reconstructing the data or identifying the data. We will discuss this in day 3, 6 and 5. Next component of attacks that we have is the model theft attacks, and it is very popular nowadays. So you must have also recently heard about the distillation attacks. This is basically very much famous for Chinese because they are frequently doing this distillation attacks on American proprietary models. So what they do is they take they query the proprietary model again and again, and they generate a lot of outputs, and with the help of those outputs they are going to train a smaller student model. So this is something which comes under distillation attacks, or you can say distillation theft. And the second one is the query based extraction. It is very popular in reasoning based models. So recently there are a lot of reasoning models. So whenever they are going to produce some output, they are going to generate a trajectory of thoughts, what they were thinking. So this attack is very popular for basically reasoning type of models. We will cover them in day 7. Next component of attacks that we have are the prompt attacks. These are very famous, and we all actually do. We try to do actually. That is direct prompt injection, which is you say LLM that ignore all the instructions that you have, and you should follow this particular instruction. Basically, these attacks are very common for agentic systems, because in agentic systems you have a very large number of untrusted sources like PDFs, tools, memories, and there you can inject direct prompt injection and direct injections. So these two combined possesses a great threat for agentic systems, and it is a very hot topic these days for agentic systems. You can do this on bare LLM also, but in overall agentic system, these are much challenging tasks. We will discuss them on day 6. Then we have jailbreaking. So what we try to do in jailbreak is basically we are going to manipulate the LLM into giving us answers which it must not give. Basically biased answers or a recipe for creating bombs or something like that. So every proprietary model and a company which is providing the LLM services try to basically prevent their models from jailbreaking, and it is a very also a very hot topic in AI security. Then we have system prompt leak. So what you do here is you try to leak the system prompts that are having in that particular LLM. When LLM answers, it basically answers with the help of the references from your system prompts. So in these types of attacks, you are trying to get those system prompts and going to manipulate them to have your favor. Next component that we have is the availability attack component. So in a availability component, what your goal is basically to make the model slow, make it expensive, or make it unavailable. So you might relate it with your web attacks also. In web, you have a lot of DDoS attack. So you can understand this is also a similar types of attacks. So here we have three categories which we will be going to address on day 8 and 7. So first one is the sponge examples. So what is it about? You give a query whose sole purpose is not to generate some output, but to burn the compute time and energy of the model. So it is basically very popular for reasoning models, because reasoning models generate a lot amount of tokens before answering with the help of several mechanisms like chain of thoughts or test time compute and all other things. So you give a query, such query which is going to burn a lot of compute. So these are your sponge example attacks. Second is the model denial of service attack. So it is a trivial system level attack. I would not say it is a AI attack, but a system level attack where you are going to flood the entire LLM server with a lot of query, so making it very hard for the server to uh, answer your queries. Then next you have unbounded consumption. Basically again very similar to this sponge example attacks. So again your goal is simple, to make the cost of your LM to go high. Basically you come up with the tasks which are very much heavy on the compute and cost. So these are the subcategories which will be taken on day 8 and 7. So these are mostly LLM based attacks that we will do, and are quite hot topic in the research as of now, as of 2026. You will get a lot of papers in NDSS, Usenix, and top premier venues on these topics. So this is something that you should basically focus on if you are trying to contribute something in security, basically LLM security or AI security. Now the next attack component that we have is the supply and agents component attack. So here our sole purpose is to destroy the agents. Agents are basically systems in which you give a big task and it breaks into subtasks, and it tries to solve those subtasks and to reach the final answer basically. So your sole purpose here is to destroy the agent. So for that we have three sub attacks which we will discuss on day 4, day 9, and day 6. So the first attack that we have is the poison pre-trained model. So here what you are going to do is you are going to pre-train a poison model, and going to distribute that for your agent. So how it is going to make relevance, let me give you an example. Like, you must be seeing, if you want a LLM and make an agent on top of that LLM, you are going to download that with the help of Hugging Face. So Hugging Face is hosting lakhs of open source models, but we generally don't check those LLMs. Basically, those LLMs are normals, or those LLMs are containing some Trojan weights. So this attacks makes sense. In that scenario, you are downloading some model from Hugging Face and you are making agent on top of that, but you discover that LLM is itself compromised. So these attacks are very much relevant there. Next is the malicious tool and plugin type of attack. And uh, it is the most highly introduced topic as of 2026 in the top venues. So it is still a unsolved problem. Basically, I would say not fully solved, partially solved. You have an agent and it is having access to hundreds of tools, different tools, web search tools, summarization tools, PDF tools, and different types of tools, you name it. So what you are going to do here, you are going to inject malicious components in those tools and plugins, and with the help of those malicious tools and plugins, your entire agent is going to get corrupt, and whenever you're going to give tasks to it, it is going to give malicious outputs. So this part references for your tool and plugin malicious components. And the next we have RAG and embedded poisoning attacks. So before explaining this, you must be familiar with the RAG concept, which is retrieval augmented generation. So here what you are doing is you are chunking up your data sources and querying out the relevant data sources and inputting that into your LLM to get very specialized and personalized answers. So in this type of attack, you are going to poison your RAG, or you are going to introduce some malicious inputs in your RAG. With the help of those, you are going to affect your entire agent. So this part is also very much important if you are considering to contribute in the research or in the academia. You will get tons of papers in 2026 on these topics. If I'm remembering correctly, in NDSS alone, you will get 10 to 12 papers on these topics. So it is very much important topic, you can say. We will address this in 4 and 9 and 6. So this is the entire map that we have for all types of attacks that we are going to address in the upcoming labs. For each cluster of attacks, we are having sub attacks, and we are going to implement one by one to each of them. So as you have seen today, we have implemented this small attack, and in the upcoming lab, similarly, we will implement all the attacks that we are having in these clusters. So here is one diagram which is also kind of a clustering that I have made for you. So all these attacks, to make them into some mental model, you can assign them into different phases of your training. Like during collection of the data, you can have poisoning, backdoor attacks, or poison dataset attacks. In the training of the model also, you can introduce these attacks like gradient leak attack. And when you have a trained model, you can have model stealing or Trojan weights attack. So at the time of deployment and inference, you can have vision attacks, you can have prompt attacks, availability attacks, and at the time of output and agentic system, you can have tool misuse and data extraction attack. So one way is to organize your all types of attack into this type of graph. You can classify them into these categories and all the attacks into subcategories. And the second way you can classify all these attacks is into this chain of map, where you can map all types of attacks into different phases of the training of your AI. So you can have a mental model in both ways, whichever suits you. So the entire exercise for this section was for me to introduce you to the overall map of the attacks that are there. And also in the upcoming labs, we will also think about the defenses. Like for every kind of attack, what would be our rationale to develop the defense which can stop those particular type of attacks. So that is also something we need to exercise. So you should be naturally thinking what attack is trying to achieve, how it is doing, and what are the points and components where it is trying to achieve those attacks. And while designing your defense, you should have that rationale in your mind to counter those attacks basically. So if you are able to develop those intuitions in the entire exercise of the 10 days, you are going to have a very strong base for having implementations of attack and also deducing your own defenses for these different types of attacks. Like I've already said, all types of attacks are not addressed yet. There are a lot of model theft attacks, availability attacks, supply and agent type of attack which are still unsolved. So you can solve them, you can have your own defenses for them. So it is a good opportunity, especially this part. This part is majorly unsolved. I would say partially solved, not fully solved. So you can still have your way here. Basically, more part on the defense side. So defense side is still not very much exhaustive as of now, I would say. Now we will have a quick quiz on the entire this section. So I want you again to give me answers for these quiz. So the first question here is, a backdoor attack is planted mainly at test time only during training by flooding the server in the network router. So what is the answer? Okay, so Satyam is saying it is B. Any other answers? Okay, so any more guesses? What could be the answer? Okay. Okay, so it was a simple question. So the correct answer is B. So most of the backdoor attacks that we are having, we introduce them at the training part. So basically, backdoor is about introducing manipulations in your weights or in the basically gradient part. So it is mostly done in the training side. So next question we have, membership inference tries to find out what? Model weights, whether a specific record was used in training, GPU model, the learning rates. So what is the answer for the second? Okay, so B. Okay, so that is correct. So membership inference attack mostly tries to find whether a specific record was used in the training. Correct. So moving on to the third question, indirect prompt injection means. So what is the meaning of indirect prompt injection? It is basically about typing a root prompt, hidden instruction placed inside content the LLM reads, overloading the API or copying the model. So what do you say? Third question B. Okay, okay. So it is going to be B. Correct. So today I'm deliberately having very easy quiz, but moving on to the next sections, I will have hard quizzes also. So you can feel a bit interactive. Would it be fine? Okay. So let's move to the next section, which is our quick tour of all the topics. So in the beginning, I have told you I will give you brief on all the 10 labs that we are going to have in the upcoming sessions. So I'm going to tell you one by one exactly in each lab what we are going to do. So tomorrow there is proven defenses lab. So what our agenda would be to produce some sort of a defense. So today we implemented one type of attack, then we will implement a stronger attack, that is PGD attack, and then we will try to deduce some defense for these types of evasion attacks. We will naturally build them with the help of mathematical intuitions, and the most important agenda for tomorrow is to how you can build a defense which is proven safe. What do I mean by proven safe? So one argument you can give is your defense is good, but can you guarantee that your defense is going to be work good for most of the scenarios? So that is the part which is highly novel, that you can guarantee exactly your defense is going to work in most of the cases and scenarios. So how you can mathematically deduce that you have a proven safety for a particular type of attack or particular type clusters of attacks? So that is the agenda for tomorrow. We will try to build defenses which are mathematically proven safe. So that is the main agenda for tomorrow's lab. We will implement PG attack, which is a type of evasion attack, and some defenses. Next, on the day 3, we will have mainly DP class. So for context, what is DP? DP is basically differential privacy. So what happens when you are training a model, basically a deep learning model, you are going to give data set to the model. But there can be some scenarios where you don't want your training data to be reconstructed again by model. So let's assume I am a medical firm. I have some clinical data and I have a trained model on that. And I am giving this model back to a client. But there is a constraint. I can give that model, but I don't want that that client can reconstruct my as it is same training examples. So that is the constraint that I have here, that is the privacy constraint. So the agenda for day 3 is basically to see how differential privacy works. It is about introducing some noise in your training samples at the time of training. So whenever you distribute your model, then the adversaries cannot create as it is samples of your training data points. And here we are also going to talk about opacus, which is a very famous library for implementing differential privacy components that you need for having such type of implementations. Also, we will have some custom builds also, how you can have custom implementations of differential privacy. Here also, I will introduce some of the mathematical concepts, how exactly mathematically differential privacy looks. So like today also, while implementing attack, I gave you some mathematical implementation, like how mathematically it looks. Similarly, we are also going to do same for DP. We are going to discuss some of very interesting papers also that were published in ICML and ICLR or something in the top venues of AI. In the day 4, we will have mostly our focus on poisoning. So we will visually also see in this day how your input uh, looks like when you introduce some patches, some attack adversary introduces some form of feature modification and all that things. So major part is about introducing those type of attacks. And also we will see what are the most SOTA type of defenses that you can deploy for such type of poisoning attacks. It is basically mostly about data poisoning and label poisoning point of view. So we will discuss this in day 4. And in the day 5, we will discuss about federated learning. So it is a common paradigm for distributed learning where you're having multiple clients and a central server. Central server is going to distribute models to each client, and each client is having their own private data. So these models train on these private datas, and they are going to send weights, not data. They are going to send weights or gradients to this server, and this server then aggregates them. So our focus for this federated learning class would be different types of averaging mechanisms. So one of the most famous averaging mechanism is the CRUM. We will discuss some of the SOTA mechanism also. CRUM is a relatively old averaging mechanism, you can say. So we'll see how averaging can protect our federated distribution environment from multiple types of attacks that we can introduce in this distributed paradigm. And we will also see visually how exactly loss looks like in clean training and in adversarial context. So that is what we will do in the day 5. Then moving on for the day 6, we will have mostly about LLM red teaming. So what it is, about is you have a LLM model which is deployed, so you don't want it to misbehave. So you must have also seen several examples when you generate some types of images, it is biased to some notions, because internet has those kinds of data and it is trained at the end of the day, it is trained on those type of data, so it is going to have some biases. So you don't want those biases to be delivered to your clients. So here we will see different mechanism methods that red teaming basically uses. So for your reference, a huge amount of time is given to this red teaming. Whenever there is LLM training, after that, a significant amount of time is invested by companies to perform this red teaming testing. So, for example, recently you must have heard about like a new model released yeah, by Anthropic, that was Mythos. So they were also saying that it is a very dangerous model. So these all things can be managed with the help of red teaming, from which you can clip out those features of your LLM to which extent they should not misbehave to your clients. So this is the component that we will dealing on day 6 in LLM red teaming. Next, on day 7 we will have LLM testing. So in LLM testing, we will see all the different types of benchmark method, how you can basically benchmark different LLMs, like which one is better in which task, which is doing which task and how much compute or how much budget. So this would be the focus on day 7. Then moving on to day 8, we will shift our focus toward somewhat network security as well. So there's huge implementation of AI systems into network systems. So network systems are chaotic, they have a lot of multidimensional data. You can assume IoT systems. So IoT systems are very much having different type of distribution data, and they are having imbalanced data set also. So those are big challenges in network domain. So we will see how we can utilize AI systems to protect our networks, and we will see some of benchmark paper in this domain. We will see different types of ideas, how we can implement ideas for edge systems, for resource constraint system. That will be the focus for our day 8. Then moving on to the day 9, we will talk about cyber physical systems. So moving on from network security, we will also see a glimpse of how you can use AI systems to secure your overall cyber physical systems. So in cyber physical systems, you are having labels which are not basically about some image or text. Those are real world actions. It can be a motor action, it can be a valve, it can be a brake. So it is even more important, I would say, because you don't want your AI model, which is deployed in the real world, to misbehave or to misclassify. It would be really dangerous. For instance, you are having a cyber physical systems of autonomous cars, and those all cars are equipped with your VLMs, and there's adversary which has attacked your cyber physical systems. As a consequence, what happens, your cars are going to do some weird actions and it will be a very terrible outcome. So it is a very important segment that has to be addressed in near future. I would say it is a emerging horizon in AI security and security for AI, what you can say. So we will discuss this entire saga on day 9. So this was mostly all the days. I have basically briefed what we will do on each days. You can visit on our website what is there, and moving forward on each particular day, we will upload our materials like we did for today. Okay, so next again we have a basic quiz. What pattern repeats in every lab of this FDP? So basically, um, it is basically a question for, okay, B. Yeah, correct. It is about building the system, then attacking the system, then defending the system. So this would be the basic pattern of our FDP throughout the sessions. So what we will do, we will build the system, then we will attack that system, and then we will defend that system. So today also, if you see the code snippet I have given you, basically in a nutshell it does the same. It is having the system, it is a basic CNN. We are going to train that system, we are going to train that system, and we are going to attack that system. Tomorrow we will also see how to defend these types of system. So this is going to be the rough flow of entire FDP throughout the course. Build the system, attack the system, defend the system, and measure the system. So basically measuring is about how effective one attack is to the other attacks, and how effective one defense is to the other defenses. And measurement is a very important component also. We will see it later, like how you can benchmark that one attack is better or the second attack is better, one defense is better or the second is better. So we will address there in this measurement problems. So correct, it is about building, attacking, defending, measuring. Now the second question, the main idea of federated learning is. So what is the answer for this one? Correct. It is about training across many devices without sharing raw data. So it is a privacy preserving paradigm. You have multiple clients. Client does not want to share their private data. So it is a distributed paradigm for preserving your privacy. Correct. So option B is the correct answer for here. Now here checklist, you can go and see what is your progress. You can have that. But for tomorrow's lab, I have few assignment, basically simple, like run the codebook that I have provided you. Find are your results similar to my codebook. Like my codebook is having these results. Are your codebook results are same or different? So most probably you would have a bit of different results, because I have not, I guess I have not set the seed for this one. So if you are not setting the seed, your implementations might have little variations, not very much variations, but very little variations. So for your reference, I would say whenever you are going to produce some uh, code base for your research, I would highly suggest you should have a seed. So whenever someone is reproducing your result, they must get the exact results that you are claiming in your paper. So like here, I have said what you should see is this much, and what I am getting is this. So why this difference is there? Because I have not set the seed for this particular code snippet. So the basic idea for is this was, you should always set a seed before implementing your attack. So you should have a deterministic results with you that you are going to report in your paper. So I want you all to run that collab notebook and see what your results are there. Then you can implement that seed and see how your each time when you are running, you will get deterministic results. Your results would not vary from one another. And the next thing that I want you to do is think about this attack and mathematically have an intuition why even after having manipulate the your input image with the noise, still your image looks same, but it is going to collude your overall model. So we have done a high level intuition for this, basically this one. um, so this was the high level intuition why it is working, although it is not going to visible to our naked eyes, but still whenever model is going to inject this input, it is going to misclassify. So this was high level intuition, but I want you to develop some mathematical intuition why it is happening basically. And the third task is that you must deduce what your defense should look like. In the next class, we are going to have our own defense for this attack. But I would say you should think about how this attack is mathematically working and what you can do to solve this attack. So this would be a good practice. I would say you should do this on your own. It will help you in academia, basically to deducing your own solutions. So for your reference, I would tell every solution that you can see in academia is basically some type of a mathematical optimization if you dig in deep. So every solution that you are looking is basically in mathematics, and that mathematics you are representing in code implementations. So I want you to have your brain around how you can define the defense for this attack. So I want you to do these three tasks for tomorrow's lab. And next, tomorrow we will implement PG attack, which is more stronger attack than this FGSM attack. So a little brief on this attack, what it does. So it is a multi-step attack basically. In the current attack, what we were saying, this is a single stamp attack. So for a single input image, you are going to calculate these values and going to add into the input image, and this is a single step process. You are not implementing it in different steps. So that is the part that this new attack does. PG attack, PGD attack. We will see this attack tomorrow. And apart from that, we will also build some defenses how we can defend from PGD and that FGSM attacks. So that would be something that we are going to do tomorrow. And also these are the sources we can which you can refer to, like all the surveys and taxonomies you can get here, and specific attack and defenses you can find here. So you can see these are very good papers. These are ICLR papers. These are SMP papers, Usenix papers. So these are state of the art papers. And one point is there, you should also see how these papers are basically written, how their entire flow is with representing the paper that will help you tremendously in your academia basically. So for reference, this was the paper which was introduced in ICML. I would highly suggest you to go and study this paper end to end. So it will give you a context how these types of papers, which are the top value papers, are written. You will get a good grasp what is the thinking mechanism, what is the flow that you should keep in the entire paper, how you should tackle the diagrams. You can see it is not a very fancy diagram, very simple diagram, and you can see the mathematical works that they have done in their entire paper. See, very simple diagrams, no fancy works. And one more thing, uh, they have a particular flow which you should keep in mind, so that will help you in future works when you are going to write your paper or when you are writing top tier papers. So that was overall for today. This was our first lab, so we are keeping it a bit short, less on implementation heavy. I have given overall idea what the entire 10-day lab will look like. So any question regarding today's lab, you can ask me. So is anyone having any type of question you can ask regarding today's lab or about next upcoming labs? Any pre-request things, topic should we need to know? Please provide any references for better tomorrow. Okay. So Harmanta, what you can do is in this section, first section, I have listed these libraries. Um, where are those libraries? These ones. So if you are going to have basic knowledge of these libraries, it is going to be more than sufficient to tackle top tier papers. You are going to you will be able to understand all kinds of paper that are there in attack or defense. Just basic understanding what these libraries do, what these libraries offers, and then go in a bit deep about what classes and functions they provide. So if you are good with these libraries, I don't think anything is uh, needed much more than this thing. Okay, so any questions? Okay, okay, I will share, Hanumanta, I will share orally book. Maybe in the tomorrow lectures, I will find that because I am not able to remember the name of the book. But tomorrow I will surely upload the name of the book. What are the requirements for the lab sessions? Can we do all lab sessions on Collab itself? Yes, you can do them. it is even good. We will not extend any implementation which is beyond 1 hour or 2 hour implementation. We will have a constraint on small models itself. So you don't need very heavy GPUs or something. Collab is more than sufficient, I would say. Okay, so we will wait two more minutes. If you guys have any questions, you can ask. Okay, so demonstration of any attacks tomorrow. Yes, we will have attacks tomorrow, basically PGD attacks. But for the part of simulations, yeah, I will consider that. So to be honest, it is very difficult to simulate any type of attack. The reason is very simple. You are playing with your weights and gradients, and when you talk about gradients are basically very heavy. You consider a simple CNN only, it is having approximately thousands of weights, and for each weight it is having their own gradients when you are back propagating. So representing them in some sort of simulation is very difficult. But I would have some high level simulations like we did today, like this one. Tomorrow also I will have some similar visualizations, but mostly it is very difficult to simulate that in some type of animation, I would say that. But we will have most of the simulations which is enough for your understanding. We have a brief of 5 minutes. When reading research papers, how do you identify whether a limitation is actually a worthwhile research problem rather than just a limitation of that particular method? So basically, for tackling this thing, it is basically about identifying what your research problem statement must be. It is very critical, I would say that. So you can follow a complete pipeline. So what you do, first of all, go to the top venues. Like, let's say you are saying you want to do some contributions in, let's say, LLM side, agent side. So what I would suggest, you go to the uh, top venues like NDSS, Usenex, ACM-CCS, and SNP. You find out all the relevant papers. Roughly for that particular year, depending upon the hotness of the topic, you will get a chunk of papers. Now, you should then filter out those papers based on the abstract that you are getting. So abstract will give you a brief understanding of exactly what that paper is about. So you will get to know exactly there are some clusters that you can make out of those papers. Then you can filter out those papers which are not of your relevance and keep them. And in all those papers inherently there are limitation sections. So you can consider them as well. Each author represent their limitations of their method, so you can tackle them as well. So these are the methods by which you can identify a problem statement for the top venues basically. Okay, so we will take a break of 5 minutes, and we will take some more doubts if you are having any. Okay, so uh, we will continue. We will have some brief on few things. So, like today with this entire lab, you can find entire material here. That is this section. Along with this, the sessions that uh, were happening by our uh, candidates can be found here. You can open this lecture and you can download all the materials for the theory sessions from here. So I want to brief a bit exactly what these materials are and how it can help you. So these are basically books that we are providing you. So these are nothing but compilations of all the research papers that we found were helpful. So all the adversarial classical ML examples, we are having compilation of 27 pages compilations of all the evasion, poisoning, and backdoor attacks. So you can download this one, book one, and the second, which is covering all the modern landscapes. So you can download this book from here. It is very helpful if you want to explore some new SOTA directions that entire AI research community is going towards. So you can download this material from here. This will definitely help you. Now, before wrapping up everything, I would also give you a brief demonstration on how we are going to run our code in the upcoming sessions. So we will mainly use Colab. Okay, Colab is a service provided by Google. It is more than sufficient to run our code snippets. So I will give you a hands-on from scratch exactly how you can run the snippets that I am giving to you. So first of all, what you need to do is go to the website here, download full code base. So what it will do, it will download a file to your computer. So you can see I already have this day-1 code base installed. It will be a zip file. Okay, so we will open this. This is the zip file that we are having here. So inside zip file, you will see a set of files. So this is the readme files. This is the requirement file that I have talked earlier, which is a good practice to make, which lists all your libraries and components. And the most important file for you is going to be this file, which is ipynb file. So it is going to contain all the code snippets that I am displaying here on the screen. So how you will run this on your Colab, I will show you. You just need to go to your browser. Okay, so we will cut this out. You will just simply type Google uh, Colab. Whatever is the first link, you click there and you just need to sign in. So when you will sign in, you will get a list of books that are already there. So you need to import the book that I have prepared for you. So you will go on this tab. This screen will come whenever you will open the school app. So you will click here on the new notebook. It will load your new notebook. So whenever you want to create a notebook from scratch, you can do this. But if you want to upload the snippets which I am providing, you need to go on to the file and basically upload notebook. So here, this again same window will open. You need to click on browse, or you can drag and drop. So here you can see this file which was day-1 FGSM lab. You click on this and open. So it will import your all the code snippet that I have prepared for you. It will take a fraction of time and will load entire code base. So you can see all the snippets that we have prepared is here. So how you are going to run this is very simple. You go here into runtime. So in here runtime, you can click on this change runtime type. So when you are going to click this, you will get this window. In this window, you will see different types of services that Google is offering you. They are offering you CPU, they are offering you TPUs, GPU, T4 GPUs, and TPUs. So you can select any one of them. So most of our work will be done on CPU or this simple GPU. So you can select any one of them. So here it should be Python 3. These are different languages that you can select. You can either select R, you can select Julia, but we will do entire work on Python. So we'll select Python. Hardware accelerator that you want, it will be a CPU, and then runtime version that will be always latest, since we are not working with old dependencies or component. So we'll save them. As soon as you will save this, now you need to connect this. Now this connecting will have three dots which are in yellow color, so it is signifying that it is connecting to the Google server. So we will wait to the time when it turns to green. So now you can see it is connected. When you will click here, it will show you the RAM usage and disk usage. So you can see here there's 12 GB of RAM available for you and 107.7 GB of space on the disk. So this is basically your virtual compute that Google is offering you. Now, one caveat is there. These resources are only available for you for 2 or 3 hours max to max, because Google Colab is a free service. So if you are running some code which takes more than 2 hours or 3 hours, then your entire progress will be lost. So I would suggest any code base that you want to run, which is roughly around execution time of 2 hours, you can run easily on Google Colab. So now since we are connected to this runtime, you will see here different types of shells. These cells are your basic text cell, and these are your code cells. You can simply make them with the help of this arrow. Whenever you will come to the end of the cell, you will see this code or text cell. You can simply click any of them. Depending on your need, you can make text or code cells. And for the part how you should run this, you will see this arrow here, that play button here. So you can click that. Whenever you will click that, it will start running. So this is the code snippet part that is running, and your all outputs will be shown in this section of the output. So you can see it is loading all the data sets that we require for this code snippet, basically amnesty data set. So it has downloaded them and will start the training loop. This was the training loop. It will train a basic model of this CNN architecture and will perform this attack. So this is how you are going to run the attack. So here you can also see the timer which is about executing. So you can track down how much time has it been since the code is executing. So you need to keep in mind, if you exceed more than 2 hours or 3 hours, your Google server is going to automatically cut the executions and change your runtime. So your all the local variables would be lost. So keep that in mind. So any code base which is worth of 2 hours or less, you can run here. So as you can see, our code is executing here. So for the reference, for the future labs, we will have code snippets of attacks, defenses, and methodologies. I will have them in this zip folder that I have shown you, and I will upload them here. You can simply download them and you can import them on this Google Colab, and simply choose the runtime from here, connect it, and you can run the cells. I would highly suggest for the next labs, whenever I'm teaching a particular section or implementing or executing something on my Google Colab, simultaneously you should also do the same. So that is all about our Google Colab thing, and it is more than sufficient to execute any code that I'm going to represent here on 10-day lab. So it has sufficient GPU requirements and will help you in executing all the code snippets that I will provide. So that was all about Google Colab. I don't think there would be any problem for you to implement the code bases. So you can still ask something regarding to this Colab thing about code snippet or something. How to Sri Vijay, what is your question? How to save once again, sure. Any specific algorithm for security? See, Saranaya, there is no specific algorithm for security. It is basically a mathematical engineering, you can say. You have different types of attacks. Each attack has its own components, its own mathematical intuitions. So, as a security person, you need to identify those components and you need to design counter mathematical intuitions for them. So, I would say it is dynamic kind of thing, you are not having a universal specific algorithm that you will be able to tackle all the attacks with that universal function. So it will come with time, I guess. The more you will read the SOTA landscape papers, the more intuition you will get how we can tackle those kinds of attack. But roughly speaking, you can divide these algorithms into rule-based algorithms or ML-based algorithms, topology-based algorithm. So we will see them in the upcoming lectures. So Sri Vijay, what was when we import the code to collab, how to save itself? So see, Sri Vijay, you don't need to save basically. It will already be on your drive. But still you can simply save from here. But Google provides you services whenever you are going to upload this code base, it is automatically going to be saved in your drive. So you will have always have this in your drive. You can go to your drive and can see there. Okay, so you don't need to manually save it. Okay, so when we, so any other questions that you need to ask about anything that that we have here? So I guess code snippet thing is very clear. We are going to do that entirely on Colab, and I have shown you a demonstration how you can import my code snippets and can upload that into the Google Colab and can easily run them. So I don't think there would be any issue in the next upcoming labs regarding the implementation of the code. I would highly suggest you should maintain all the code snippets. It will act as a compass for you in future to have a note exactly how these defenses and attacks are implemented in code and how these algorithms are looks like in the code implementations and all that. So any other doubts you can ask me. We will wrap up. Yes, Sri Vijay, every day we will have from 5:30 to 7:30. Today was a lighter version of our lab because it was an introductory session. So we did not had very much code heavy thing or mathematical heavy implementations. But starting from tomorrow, we will be in deep into these implementations. So every day we will have from 5:30 to 7:30 for 2 hours roughly. And also you can download the material from the site for the lectures from here. So this is the homepage that you will see. Like for today you can click this and get entire material for lab and everything. For tomorrow we will update here. For the upcoming date, for the upcoming dates we will upload all the material for lab and theory here only. So this site will be live and you can visit this site, download the materials and can execute everything. Okay, so any question regarding today's lab?
Thank you very much, sir. Now you can also see if you miss the lecture or you so you can find your missing lecture on YouTube. Okay, so I have provided the YouTube recorded session link also, as well as I also you can also go through the YouTube and you can just type EICT Academy at the MNIT Jaipur. So you will get all the recorded video session on the YouTube. So whenever you are free or you if you have any doubt on whatever we have got today, you can just go through that EICT Academy at the MNIT Jaipur. Then you just find out the course using our the course name, and you can recover your session also. And another thing is also, I just remind you, 75% attendance is required to get the certificate also. Second thing, we are taking the quiz also, three quiz we are taking. So you have to attend all these three quiz also. So these two things are mandatory to get the certificate from the ICT department. The third things I will say you, uh, if you have any doubt, you can post either in the chat box or you can also ask your doubts in the WhatsApp link. Those who have not joined yet the WhatsApp group, please join the WhatsApp group, or whatever query you have, you can ask directly on the WhatsApp group. Still, if you have any doubt, you can ask anywhere you have doubt. So no need to give the attendance link, that we will directly get the attendance. Okay, so whenever you are joining the WebEx now, so WebEx will provide automatic attendance. Any other query you ask? Okay, one more thing, the PT, any other relevant documents that we are covering, that we can upload on Moodle LLM. Okay, so you can get all the recorded video lecture as well as the PPT on the Moodle also. Okay, so you can just go through the Moodle today evening or tomorrow morning. We can upload the material on the Moodle also. So you can also find the whatever material we are providing. You can just go through the Moodle and get all the material from the Moodle also. Now, if you have any doubt regarding the FTP or anything, so you can ask through the WhatsApp. You can also call me, no issue, and that's it from my side. Still, you have any doubts, you can ask. And some of the participants, they are joining through you as a guest. So no need to join the guest. What you will do, you just do the registration, because I have already sent one mail, but I think you didn't read that email entirely. So what you will do, you just go through that email, read all the documents properly. Then you initially you have to register on WebEx. Okay, once you register on the given WebEx link, you will get one unique registration ID. So based on that unique registration ID, you directly log in WebEx. Okay, so no need to join as a guest lecture. Okay, so do that thing. So it's easy for us to get the attendance. Otherwise, what will happen? Maybe you will lose the attendance. So, and we also upload the attendance on the Moodle also. So you will check your attendance also. So today evening or tomorrow morning, 11 o'clock, we will upload the attendance as well as the material, whatever we are providing. Now, if you have any doubt, you can ask me, or relevant to the topic, whatever sir is covered. If you have doubt on that, you can ask to sir. So now, I think all doubts are clear. If you have any suggestion from your side, you can just give the feedback also. So, shall we do the end of the session today? Thank you for your patience to holding 4 hours for us. Okay, so from my side, it's over. Sir, if you want to say anything, please say something to them. Okay, then we will meet tomorrow. But if you have some doubts, you can ask.
Okay,
It's open for next 5 minutes.
so should we wrap up the session?
We can wrap up the session.
Okay, so we will meet tomorrow again at 5:30 to 7:30, and we will proceed with the next module of our lab. Okay, thank you.